Welcome back. Last time I talked a little bit about the vector network model. Sometimes you don't want to calculate distances based upon as the crow flies or a straight shot. Sometimes you're not calculating distances, but you're more interested in things like times or some other type of cost or impedance. In those cases, what you need to do is you need to deal with a network model. A network model is a combination of lines and points. We're going to call the lines edges. The points are going to be called junctions. They're topologically connected so that you're able to do what's called linear referencing, and you're able to measure things along that network and calculate distances, costs, impedance, time between one point and another. Okay, there's a lot of things you can do with these network models, and I thought I'd go over a couple of the applications that are illustrated in your text. There are a bunch of different analyses you can do with the network analyst, and again, I've said how complicated this network analysis is. It's an advanced topic in GIS, but so that you get a better idea of what kind of things you might think about being able to do with networks, here's a few. Optimum route. Pick point 1, point 2, what's the best way to get from point 1 to point 2? Which is the closest facility to where I am or a spot that I'm interested in? What are the service areas associated with certain points? And if I have a delivery route, what's the best way to get my deliveries done in minimum cost, time, distance, whatever? And if I have a bunch of existing spots and I want to put a new spot in, how do I allocate new and existing locations in terms of maximizing my return on that? Route analysis, shortest distance between A and B. That's the basic straight line network analysis, and in the last video I showed you how the algorithms basically walk out along the network points and calculate the times or the distances from each point to each adjoining point, finding the optimum route by the shortest distance or the shortest impedance between the points. That's a straightforward one. You use it on Google all the time. Okay, this is the traveling salesperson problem, and this is one of the more common problems, and the computer scientists spend a lot of time trying to write algorithms that can do this more efficiently or more effectively. So you can imagine this example being maybe a warehouse here in San Francisco on the peninsula, and maybe you have 3 different trucks, 3 drivers at your warehouse, and you have all of these customers over in the East Bay and up north and down on the peninsula. What is going to be the best set of routes that your vehicles should follow to minimize the cost or the time or the gas expenditures, the distance for all 3 drivers? And this is called the traveling salesperson analysis, and it's a really complicated algorithm. So what the algorithm does is it just gives you a really good guess as quickly as it can, as opposed to trying to really optimize things. Closest facility. This illustration from your book shows police cars and crimes occurring, and the idea behind this is if a crime occurs right here, which cars does the dispatcher send to respond to that crime? So the dispatcher is going to send the cars that are going to get there most quickly, so that's probably going to be a time impedance. It's going to know where you're at and where the cars are, and it's going to be able to calculate which vehicles to send to which location. This also might be where you are right now, and these might be ATMs. What's the closest place I can get money from an ATM? Or where's the closest Mexican restaurant? Or where's the closest whatever? Closest facility analysis. Origin destination cost analysis. What that does is you give it a set of input points on the network, and it goes out and it calculates the distance on the network, linear reference, not a straight shot reference, between each point and every other point. Now what this shows is straight shots, but what it's doing is it's calculating a network distance between each point and each other point, and it stores that in the attribute table for each of the points. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 cities. We're going to get a table that has those 9 cities, and it has a total time column in this case, because what we're interested in is time, not distance or cost of some other things. So you can see that from Milwaukee to Detroit is 355 minutes, and so the network must have speed limit information all along the network, and it routes you along the route that's going to get you from one point to the other the most quickly. It's going to display it this way, but what it's doing in the background is it's calculating it this way. And so for each point and each other point, it's calculating a distance, a shortest time, a shortest impedance between that point and all the other points. Service area. This is another one that's pretty useful, where you can imagine, let's say we have trucks. Where do we put our trucks in these cities? Well, we put our trucks in the city that's going to be closest to the service area for that truck, and sometimes service areas will run into each other. So if we have a customer over here, that should be serviced by the truck that comes out of this spot. These aren't straight circular straight shot distances. These are calculated along a network, right? So this network could be mileage, it could be time, it could be gas expenditures, things like that. So where do we split up the network in terms of who gets to service which customers? This is service area analysis. Location allocation gets even more complicated. You can think of this as existing facilities. So here we have existing facilities, 1, 2, 3, 4, 5, 6, 7 existing facilities. Suppose we want to make a new facility. Where's the best place to locate our new facility so that we don't take away area or customers from our existing facilities if possible, but we serve customers that aren't readily served by our existing facilities? So you're locating and allocating. You have customers and you have locations. You're deciding how to locate places that allocate your customers optimally. And so you can see where this is really a complicated analysis. And you can also see where almost all of these applications can involve business concerns, and money concerns go hand in hand. So there's a lot of money involved in network analysis. Geometric networks, that was a transportation network. Remember, geometric networks are usually directional, so they only go in one direction, and you can see in this example all the arrows are pointing down towards this, which is called a sync point. These points that are at the back end of the network are the source junctions, and then this is a sync junction. So you can use a geometric network to do a lot of things that allow you to do things like determine flow direction, what's upstream and what's downstream from a point, how much is coming in from upstream points, how much will be going to downstream points. And suppose you have things like a network that's an electrical utility. You might have an outage, and you can make an outage occur at a certain point, and you can see how many people are impacted by that outage downstream, things like that. It's also good for things like hydrologic analyses and flow contamination analyses, things like that. Okay, a lot of this stuff is really powerful, and if you want to look at yet another video, there's a set of videos put out by Penn State that are called Geospatial Revolutions. And episode 2, the video in episode 2, talks about how UPS uses the network model to attempt to optimize their delivery, get things to the customers as cheaply and as efficiently and as optimally as possible. And you'll see when you watch this video how involved this is and how it's really quite an advanced analysis. Okay, next time I'm going to talk about a couple of different data sets that you can get from the government. The Tiger files are going to allow you to do network analysis for transportation networks. The NHD files, National Hydrology Data Set, are going to allow you to do network analyses for surface water. And then this geocoding, that's about giving the computer an address and having the computer find that address on your network. So that's what I'll talk about in the next video.